Some of the functions that we've discussed already include polynomial functions. As an example, if we had the function f of x equals 3x squared plus 4x plus 2, this is an example of a polynomial function. This is a polynomial. It's just a sum or difference of terms. So for our polynomial function, a few things that we know is that the domain, the possible x values or the possible input values, will be all real numbers. If we wanted to write this in interval notation, it means that we can start at negative infinity and go all the way to positive infinity, and all those values in between there are things that we can use. So we can input any of those numbers for x. The range is going to vary depending on the function. But something that we want to remember is that for a polynomial function, the domain will always be all real numbers. We also said that we could look at the leading term, which in this case is 3x squared, and that would tell us what happens at the ends. This leading term is positive because we have a positive 3 here, and it's even because we have an even power. And for positive even, we said that the ends have to both be up. If it were a negative 3x squared, the ends would be doing the same thing, but they'd be going both down. The behaviors that we noticed for polynomial functions were really generalizations of what happens with a power function. But what is a power function? A power function is a function that has a base, that's a variable, and then a power, that's some number, and it has some constant that we're multiplying by. The n in this case, again, we said was the power. And the a was the constant. We call it the constant of variation. So as an example, if I had 5x squared, 2 would be the power, and 5 would be the constant of variation. For power functions, there's some general patterns that they fall into. X squared is going to look something like this. X to the fourth is going to look something like this. X to the sixth is going to look something like that. And so if you notice, what they all have in common is that there's a mirror in the middle here, that this line right here, the y-axis, acts like a mirror. So what we can say for even functions is that for even functions, that they are symmetric with respect to the y-axis. So the y-axis would be our mirror. So for x squared, x to the fourth, x to the sixth, x to the eighth, and so on, for any even function, that is going to be symmetric with respect to the y-axis. For odd functions, their symmetry is different. This is an example of an odd function. This would be x to the third. If we say x to the fifth, that would be something like what x to the fifth would look like. X to the seventh would look like something like that as well. What all of these have in common is that their symmetry is here, that this point acts like a mirror. So what we would say here is that for odd functions, they're going to be symmetric with respect to the origin. So odd functions are going to be symmetric with respect to the origin. So x to the third, x to the fifth, x to the seventh, x to the ninth, etc. Notice that all of these have odd powers, that they're all going to be odd, and they're all symmetric with respect to the origin. So why exactly are power functions important? Suppose we had f of x equals 4x cubed, and we had to do something in calculus called the derivative. F prime of x, in this case, we would take the 3, multiply with the 4, and we would get 12. We keep the x, and we subtract its power by 1, and that would make it 12x squared. If we had another example, let's say g of x equals 8x to the fifth, and we want to know what its derivative is, we would say 5 times 8 is 40, and then we would keep the x, subtract 1 from the power, and that's x to the fourth. This is the power rule for derivatives. So we need to be able to rewrite as power functions expressions so that we can calculate this derivative. As an example, suppose that later on in calculus, you're asked to work out the derivative of this. Well, we need to know how to rewrite that as a power function. Anytime you have a root can be written as a fractional power. So because we have this root here, we know it's going to be x to some fraction. The index is the denominator. So 4 in this case is the denominator. The power is the numerator. So x to the 3/4 is the same as what we started with, which is 4th root of x to the third. So suppose that we had the function f of x equals square root of x, and we need to rewrite this as a power function. We know that the base is x. We know that we're going to have a fraction because we have a root. We know that this is the square root, and as we know, square involves a power of 2. So there's an index of 2 here that's not written. So that means the denominator is 2. The unwritten power on the inside is 1, so it will be x to the 1/2. So here we know, again, the power is 1/2, and the constant of variation is the coefficient. And keep in mind that there's no number in front, so we're going to make that 1. So suppose that we're given the following function, f of x equals the 6th root of x to the 5th. Again, it's a root, so we know that it's going to be a fractional power. The base is x. The index is 6, so that means we're going to have a denominator of 6. The power is 5, so that means that we're going to have 5 in the numerator. So x to the 5/6 is what this would be rewritten as. That means that our power is going to be 5/6, and our constant of variation, as in the previous problem, is 1, because there's an unwritten 1 here when there's no number in front, when there's no coefficient. We need to remember something else as well that's useful in some of these problems. That if we have 1 over x squared as an example, this means x to a negative 2. If we have 1 over x to the 5th, this means x to the negative 5th. If we have 1 over x to the 4th power, this means x to the negative 4th. So what would 1 over x to the 7th power mean? It will mean x to the negative 7th. So anytime we see our expression in the denominator, what it really means is that we're dealing with a negative power. So suppose that we had something of the form k of x equals 1 over the third root, so we know we're dealing with a fraction, of x squared. The fact that we're dealing with something in the denominator here, what does that tell us? That tells us that we have a negative power, so it'll be x to the negative something. The denominator of that power would be 3, and the numerator would be 2. So this is the same as x to the negative 2/3. What exactly does continuity mean? Well, continuity, stated very briefly, just means that we should be able to draw in a smooth, continuous motion whatever our graph is, and we don't have to stop. So this is an example of something that is continuous. Something that is discontinuous means that we have to just stop. So as an example, let's say I have a curve that looks like this. I keep going, and there's a hole right here, which means I have to lift up my pencil, and then I have to keep going. So this is an example of something that is discontinuous. It's not all connected. Another example of something that is discontinuous is, so suppose that we have a curve that continues, but it is never going to cross this line here. And then we jump over to the other side, and now this is what the curve is doing. So this is an example of something that is discontinuous. So both of these are discontinuities, but they have different names. This one is removable because I can redefine my function to say at this particular location where there's a hole, let me just put that value back in. So this is a removable discontinuity. I can fill it in, basically. This, on the other hand, is an example of a non-removable discontinuity. And what we mean by that is just that there's no way for us to fix this with a simple function definition to make these connected. We already looked at graphs for things like x squared and x cubed. And we noticed that for each of these, that they were going to be continuous. Whereas if we had something like 1 over x squared, its graph would not be able to accommodate a 0 here. So we cannot put 0 here. So that means that there's an asymptote right at 0. So this line right here, we would never have a value on that line. We would have to have an asymptote. So our function could get closer and closer and closer, but never actually reach there. It could also similarly get closer and closer and closer, but it never would actually reach that red line. Also, this function would never equal 0 as well, because if you think about it, what we're saying is that we're taking one whole thing, we're dividing it up into so many parts. So if we took one whole pizza and kept cutting and cutting and cutting and cutting, making it smaller and smaller and smaller and smaller, would we be able to ever reach a particular number of cuts where the pizza would disappear? No. So that means that this will never equal 0. So what that means is that for positive powers, so for +2, +3, etc., that these particular functions will be continuous. But what can we say about negative powers? For negative powers, we know that, as an example, x to the negative 2 cannot equal 0. So what happens is that we have values that get closer and closer and closer, but they never actually reach 0. Also, we know that we can't input 0. We have to exclude 0 from the domain. So judging from how our graph looks, we know that this means that our graph is going to be discontinuous. And our discontinuity here is going to be something that we cannot remove. It's not like there's just a hole that we can fill in. So our discontinuity here is non-removable. So this is what a non-removable discontinuity looks like. And it's at x equals 0.